Today I want to look at this idea of the probability distribution function. You're like, wait a minute, is this statistics all over again? Yes, it is. I'm trying to link the ideas of calculus and statistics together. So to do that, I'm going to actually ask you to do some statistics first. So look at my example here where I said there's a survey and it finds this data about the average age of a rented car. And we've got age, and then we have probability of that age happening. And then I've also taken this data here and I graphed it out in a probability distribution histogram. That's right, don't say bar graph, call it a histogram. The statistics students know why. And I want you to use it to evaluate or actually estimate the following probabilities. So if I ask you for the probability of x being the random variable, in this case the age, be between 0 and 4, all of my great statistics students will say, oh yeah, take the values from here to here and add them up. Perfect. So 0.2, 0.28, 0.20, 0.15, and add them up. That's 0.83 or 83%. Yay. Okay, try the next one then. The x is greater than or equal to 4. You guessed it. That's this region here, so add those up and you'll get the answer. Good. Or you could have done the complement, remember that stuff? 1 minus the probability of x being less than 4, and you could have done that as well. You'll still get the same answer. Oh, by the way, the probability less than 4 is actually what we just calculated from part I, so I could have just done this and that would have gotten me the same answer. The probability of it being between 2 and 3.5. Now, this is kind of interesting because here's 2 to 3, but what about 3.5? What's up with that? So in this case, we have to kind of do an estimate, and what we can do is say, well, from 3 to 4 it's 0.15, so maybe 3.5 will just be half of that region, and you can make that estimate and get an approximation of 0.275. Finally, what about it equaling 4? In this case, when it's equaling 4, it's right here. Really, there is no probability, nothing right here. So equaling 4 really is 0. Okay. I want to make a note here too that says if x was a continuous random variable, then x can assume infinitely many values. So therefore the probability of it being assuming any specific value like x equal to 4 is 0. Okay. Alright, now I'm going to show you the histogram again, and then I want to draw kind of a curve that kind of connects them together. Here's your lovely curve. And I want to tell you that this curve is the graph of some function f, right? In calculus we always talk about curves and functions. Well, we have a special name for this function, or it's called the probability density, or sometimes it's called the distribution function, better known as PDF. No, not the Adobe PDF that you create when you print a document, but PDF, the probability density or distribution function. Now we take the domain of this function f to be between 0 and infinity, because this is the possible range of values of that random variable, meaning that random variable, in this case was age, that can take, because age technically can be from 0 to infinity. Now what about using calculus? How do we find this then using calculus? And how do we find that using calculus? Well, if you think about what we've learned about calculus and curve, and oh, did you think about something called the area under the curve? If you did, that is correct, because that's really an integral. So ultimately, the probability from 0 to 4 really is the integral from 0 to 4 of the function f of x. And similarly over here, we have the integral from 2 to 3.5 of f of x dx. Now remember, in statistics, the probability of everything added up together must be 1. So the probability of having an age of a car between 0 and infinity must be 1. And therefore the probability between 0 and infinity is really equal to the integral from 0 to infinity of f of x dx. And this value must be equal to 1. Alright, so I hope you can kind of see a little bit of the connection between calculus and statistics. And that draws us to the conclusion on the next page of our notes. And that says, well, in order for a probability density function to exist, it's a function that's defined on an interval, and it has to have these properties. Number one, the f of x, or the probabilities, always have to be bigger or equal to 0. And number two, the integral from a to b, so from the lowest value to the highest value of the random variable, when I integrate that with the function f of x dx, this always has to be equal to 1. Okay? A and b can be any number. It could be both infinite if we want it to be. And if that happens, of course, we get an improper integral. Remember those times? I think that was lesson 7.1 in our notes. So using a probability density function to compute probability, the idea here is this. If you want, or if you have a continuous random variable x, and it creates a probability density function called f, then if you want to find the probability of it being between c and d, it's just the integral between c and d of the probability density function f of x dx. Okay? So, let's take a look at this example here. Suppose that you have a troubled savings and loan institution. Think of it like a bank. And they're failing continuously, oh no, at a rate of 5% per year. Okay? What is the probability that a troubled savings and loan institution will fail sometime within the next t years? And you can assume that you started with 100 of these types of institutions. Now, when I see the word continuously compounding, you should remember maybe back in pre-calc 12 days or even calculus days, that's this function c, or a, e to the rt. Okay, remember that? Think of it as an exponential function. In this case, if I think about the number that are left, okay, we started with 100 and we're decreasing it by a rate of 5% per year, so that's actually negative 0.05 t. If that's what's left, then how many have failed? Well, that will be the difference between the starting value, 100, right, starting, and you want to minus how many have actually are left. So that's the number we just did here. And we have this expression that represents the number that have failed. The next part says, well, can you tell me the percentage that would have failed by that time? Hence, really, the probability that's asked for that question. So the probability in this case is really the number that have failed divided by the number at the start. Well, how many failed? Yeah, we got that. 100 minus 100, e to the negative 0.05 t. And how many were at the start? You got that, 100. And I guess I can factor out 100 from the numerator. And that leaves me with this lovely expression. 1 minus e to the negative 0.05 t. Nice. Nice. So, if x is the number of years a randomly chosen troubled institution will take to fail, then we have just calculated the probability that x is between 0 and t. That is, that the probability... Oops. Oh, what just happened there? The probability of 0... of the random variable x between 0 and t would be somewhat equal to what I just said above. 1 minus e to the negative 0.05t. Now, remember how we are supposed to be able to also use an integral to figure this out? So if this is my result, think of this as my result. Okay, what is the function that I would have to use to integrate to get this result? So I'm really asking you this now. What am I integrating here to get this as an answer? And what is the opposite of integration? I hope you remember it's the derivative, right? So if I started with this as the function, what is my derivative? Y prime. That's the derivative of 1 is 0. The derivative of negative e to the negative 0.05 is the function itself, right? With an extra factor of negative 0.05 chain rule. And that just gives us 0.05 e to the negative 0.05 t. And therefore, really, that's what I should be putting into this little box. And therefore, the probability density function is 0.05 e to the negative 0.05 t. And our limits here, because we have the probability beginning at 0 and ending at t, there you have it. Okay? So thus, this probability is really just equal to the integral from 0 to t of 0.05 e to the negative 0.05 t. And so we use this particular function, f of x, as, once again, 0.05 e to the negative 0.05 t, as a probability density function to model this situation. Hey, look at this. Integrals, derivatives, nice. So, continuing on with this example, in example number 3, it says, does this function satisfy the mathematical conditions necessary for it to be a probability density function? And once again, what is a probability density function? There are two caveats here. Here we go again. A, the function always has to be bigger or equal to 0 for all values of x. And B, the integral of it from the lowest to the highest value must be equal to 1. So let's check out these things. So part A, is the function always bigger or equal to 0? Well, remember the function was given by this expression. It's an exponential, even though the exponent here is a negative. That's still okay because the graph probably looks like this, and therefore the answer is yes. It is satisfied. So A is good. So now the question we need to do is we need to check to make sure that the integral from A to B of the function does equal to 1. And in this case, A to B would be the integral from 0 to infinity of the function 0.05 e to the negative 0.5 x dx. Excuse my writing there. And the question I have for you is, well, how do we do this? If I want to do it properly, remember this is an improper integral, so set it up like this with a dummy variable. I'll use b. I hope this stuff is coming back to you now. Taking the antiderivative of e to the x, that's just the same function e to the x, except don't forget there's an extra factor you have to get rid of, which is dividing by the 0.05. That's beautiful. And then we integrate this from 0 to b. Remember this stuff? Yes, we still have the limit as b approach to infinity. We have the limit as b approach to infinity, e to the negative 0.05b. Negative, got a negative. Minus, of course, in this case, negative e to the negative 0. When I plug in infinity, e to the negative infinity, that's just going to be, what is e to the negative infinity? E to the negative infinity, that's like 0, isn't it? Yeah, that's like 0. And then these two negatives become a plus. E to the 0 is just 1, so woo! We're saved. this does equal to 1. That works too. So it satisfies these two conditions, so therefore I'll say yippee, or I'll say yes, this is a probability density function. Yay! Now just a quick note. There's nothing really special about that number 0.5 because any function of this form where that 0.5 is a constant in front, which is also the 0.5 next to the variable x, is and will always be a probability density function. There's an actual special name for this type of function. It's called the exponential density function. So an exponential density function always has it where the constant in front is equal to that constant factor next to the x. Of course, that constant factor will have the negative sign in front, because then the graph actually goes downward. Concave down. All these terms from calculus again. So now just continuing with example number 2, find the probability that a troubled institution, meaning this bank, will actually fail between 2 and 4 years. So ultimately I'm asking you to calculate the probability of that random variable x, the time it's going to fail, to be between 2 and 4. And yes, that is equal to the integral from 2 to 4 of the function 0.05 e to the negative 0.05 x dx. And we can calculate this quite easily. We did it already, so we can just anti-differentiate this. Extra factor of 0.05 in our denominator. Negative. Those cancel. Plug in 2 to 4. We will get e to the negative 0.05 times 4 minus, oh, I found a negative in front. My apologies again. Negative e to the negative 0.05 times 2. And if you do this on your calculator, calculate, I got an answer of 0.086. So only about an 8.6% chance of failing between 2 and 4 years. Okay, what about this next one here? What's the probability of the last 5 or more years? So the probability of that random variable x being bigger or equal to 5. Here you would take the integral from 5 to infinity of 0.05 e to the negative 0.05 x dx. Or, anyone think of another way of doing it? Think about the idea of the complement. That could be just taking 1, which is the entire probability of all the possible things happening, and subtracting from that the complement, which would be from 0 to 5 of the function 0.05 e to the negative 0.05 x dx. That would also work. Regardless what you choose, I did the calculation already. I know you're eagerly waiting for the answer, so here it is, 0.779. Okay, now perhaps the most interesting class of probability density functions are the normal density functions. Yes, the normal density function. Those of you taking AP psychology, you've probably seen this before. I know Miss Burbridge always talks to me about the normal distribution and standard deviation, all that kind of stuff. So the normal distribution really is a function, and it has the function of this form. Yes, this is the formula behind it. Scary. 1 divided by sigma times the square root of 2 pi e to the power of this ugly expression, which is a negative, of x minus the mu, which is the mean all squared, divided by 2. I believe that's sigma squared. Okay? So mu, you guys are in statistics, know that's mean, and then sigma, called the standard deviation, how far you are away from the mean. They can be any positive real number. And if you actually graph this out, you'll get this very talked about graph. Notice that it is concaving up, then an inflection point happens, woo, at mu minus sigma, and then it becomes concaving down, and then also concaving up after mu plus sigma. Do you guys remember these ideas of 1 standard deviation away from the mean? Remember that? it's one standard deviation, how much that covers. I think many of you have seen the idea of this as one standard deviation away from the mean. That's 68%. Remember that? And then if you could draw something with two standard deviations away, do you remember what that was? One standard deviation, two standard deviation. That's quite a lot of the curve. Yes, that gave you 95%. And do you remember three standard deviations? Yeah, if it was three standard deviations, I won't draw that. But that's within, I think, 99.7% of the data occurs there. So note, you'll see the normal density function applied in many situations that involve measurement and also testing. For instance, repeated imprecise measurements of length of a single object, or a measurement made on many items from an assembly line, or a collection of SAT or AP scores tend to be distributed normally. It is partly for this reason that the normal density curve is so important in quality control and also in assessing the results of standardized tests. But here's a drawback too. The antiderivative of the normal density function cannot be expressed in any commonly used function. So if I ask you to do it by hand to integrate, I'm so sorry, you can't do it. And so thus we need to use the graphing calculator to help us calculate the integrals involving the normal density function. So pull out your graphing calculator now if you can, so that you can also do this. Let's look at example number 5. Pressure gauges. Yeah, you better check them before you sell them, because if they're not accurate, that can lead to catastrophic problems. A worker here uses it to measure the pressure of a sample of compressed air. And it's known to be at a pressure of exactly 50 pounds per square inch. Okay? Think of, like, you know, your bike tires, all that kind of stuff. There's pressure, and the measurement for pressure is pound. Oops. Great. Where'd it go? Pounds per square inch. Yeah, here we go. If the gauge reading is off by more than 1%, which in this case 1% of 50 would be 0.5, the gauge is rejected. So assuming that the reading of the pressure gauge under these circumstances is a normal random variable with mean 50 and standard deviation 0.5, so that's your mu, and here's your sigma, find the percentage of gauges rejected. So ultimately, what probability are we looking for here? We're looking at the probability that the gauges are what? Well, we want to keep these, right? So what must it be equal to? Well, you want it to be really equal to 50, but there is this leeway of 0.5 pounds per square inch. So really, if a gauge is reading a number 49.5 or higher, or actually not higher, but less than 50.5, then these are the gauges we keep. And they're the good ones. So the question is, how do we calculate the probability of that happening? Well, it's now the integral from 49.5 to 50.5 of that lovely formula from up top. Okay? So it's 1 divided by sigma, and sigma is 0.5, times the square root of 2 pi. This is the exponential function, so e to the power of negative x minus mu. Mu is the mean, so x minus 50 all squared, divided by 2 times sigma, which is 0.5 all squared as well. And then we have dx. Okay, so just note this whole thing here is an exponent. Okay. And so I'm going to ask you to punch this into your calculator right now, and you're going to do it. And I'm going to tell you, bam, the answer is 0.6827 from the calculator. Now, you might have been wondering, hey, Mr. Lee, we talked about this standard deviation of 0.5, and it just so happens that if I add 0.5 to 50, I get 50.5. And if I subtract 0.5 from 50, I get 49.5. So really here, this probability is also the idea of being one standard deviation away from the mean. And that exactly is what we just got with this number here, 68.27 or 68%, right? 68%. Same thing. So if I'm asking for find the percentage of those rejected, then I should then continue now and say those that are rejected. Well, that's just 1 minus the probability of those that are accepted. And that would be 1 minus 0.6827, or approximately 0.3173. How about 32%? That's almost 1 in 3. That's pretty bad for a production line. But nonetheless, that's the answer here. Okay? Any questions? Well, you really can't ask me, but you can always email me and all that too. But yes, I'm hoping you can see how calculus and statistics are going hand in hand. Now, I've got a few more things I want to do with you. I know this is a pretty long video, but two more pages, I guess. Yeah, well, let's see if we can do these now. I want to talk about this idea of mean or expected value. Because you're like, what? Hey, what's that mean? Well, you can actually define these using calculus as well. So if x is a continuous random variable with a probability distribution or density function of little f, defined on an interval with a possible infinite endpoint of a and b, then the mean is really equal to this. It's the actual variable x multiplied by f of x. So the expected value is also called the average value of x. It is what we expect to get if we take the average of many values of x obtained in different experiments. So the question I have here says, why is e of x given by that integral formula from above? So why is it this thing here? So I want to just talk about this, but we've learned this concept before in calculus, where if I just, for simplicity, take the domain of f as a finite interval between a and b, and I want you to break up that interval into n subintervals, each of length delta x. So think about something like this. Remember how we did that before? Delta x, another delta x, another delta x. Does this look like a Riemann sum to you? So now if we look at the probability of seeing a value in a particular delta x, it's really approximated by the height of the function. Remember, so if I took this one particular one here, it's approximated by the height of the function, this f of x of k, that's the height, multiplied by delta x, which is the width. And if I think of this as the fraction of times we expect to see values of x in that range, these values really are all close to x sub k. And then they contribute approximately x sub k times this area to the average. And if we average together many observations of x, then we can add them together to get this lovely expected value, which is really the sum of all of these x sub k's multiplied by the f of x sub k times delta x. And once again, remember, as these approximations get better as n approaches to infinity, so really we're putting the limit as n approaches to infinity in front of the summation. We've done this before in calculus too. That just then turns this limit and summation into the integral sign, which is the formula that we're using right now. Okay? So I'd like to look at example number 6 now. So continuing with our whole idea about those banks failing and all that kind of stuff, given that the troubled savings and loan institutions are failing continuously at a rate of 5% per year, how long will the average troubled institution last? Well, really I'm asking for average, which means I'm asking for the expected value. And the formula we know is the expected value is the integral from a to b of x times f of x dx. So in this case, the integral goes from 0 to infinity. of x times, and remember f of x, what was that? That was 0.05 e to the negative 0.05x dx. And if I want to write this a little bit nicer, perhaps I will put the 0.05 in front. And now the question is, you have to now integrate this. Oh, great. This one you can do by hand. You do not need a graphing calculator. So I'm going to ask to see if you remember what integration technique we should use to integrate 0.05x times e to the negative 0.05x dx. Oh boy. Think back. Think back. Did you hear me say times? And if you said in your mind, oh, it must be integration by parts. Oh yeah, you are correct. And I would have split the parts like this. Remember, uv minus integration v du. The idea of Lipit, where the u should be logarithms. We don't have any here. Inverse trig, we don't have it here. Polynomials, yes we do. There's the 0.05x. So remember, the idea is then to figure out du 0.05 dx. To figure out v, we anti-differentiate, which is e to the negative 0.05x divided by negative 0.05. And then, of course, we'll plug it into our UV, ultraviolet, integration of v du, voodoo. And if we substitute the values in, 0.05x times v, e to the negative 0.05x, divided by negative 0.05, minus the integration of v, e to the negative 0.05x, divided by negative 0.05, times du, 0.050 dx. I like that. Oh, beautiful. Oh, beautiful. I have here negative x e to the negative 0.05x. I have here the two negatives become a positive, and the 0.05s cancel out, so I just have this. Perfect. Because now I know I can integrate that nice and easy. That's just negative x e to the negative 0.05x, just copying that down. And then here, this is the integral. We've done this so many times now. And then I want to evaluate this whole thing from infinity to 0. I know I'm not doing the proper notation, I'm so sorry, but I'm running out of space. And if you do this, you plug in infinity, I believe you'll do all the work. And I know you don't want to do it right now because you're lazy. But I'll just give you the answer anyways. 20. Interesting. The average institution will last 20 years. So note that this answer in this question is 20. 20. It also seems to be the reciprocal of the failure rate. Remember the failure rate was 5%? So 5% is just, what? 5 out of 100? That's actually 1 over 20. So interestingly enough, that for this particular exponential density function, the expected value of it is always equal to 1 over a, the reciprocal of the failure rate. And so this just happens to be the mean, or the mu, because that's what expected value actually is. Now let me just finish off with one last terminology from statistics. How about the median? So in statistics we have this definition for the median, that's like the middle. And so if I talk about a continuous random variable set, the median, of course, is the number m such that half of it's to the left of it and half of it's to the right. If f is a probability density function, and it's defined on a and b once again, then we can calculate m by solving this lovely integral. I can start from the leftmost point a and go to m, which is the median, As long as this integral value equals to half, I know m must be the median. And visually or graphically, it's really the vertical line that cuts the area under the graph into two equal parts. So finally now with example number 7, I'm going to ask us to take a look at this. The time in minutes between individuals joining the line at the Burnaby post office is a random variable with the exponential distribution of this now. F of x equals to 2e to the negative 2x. So notice this is like the exponential density function, a e to the negative ax. Okay, so it says find the mean and the median of time between individuals joining the line. Okay, we're going to assume, of course, time is in minutes in this case. So let's do the mean first. Notice I said f of x is equal to 2 equal to negative 2x, which is really just an exponential density function. How would I quickly find the mean then? The mean is just equal to 1 divided by the a value. So in this case, that'd be 1 over 2. So that means a person will join the line every 30 seconds on average. So therefore, a person will join this lineup every 30 seconds on average, right? The mean. Well, what about the median? Well, the idea of the median, once again, is I want to take the integral, and we're starting at 0 for this density function. Notice that starting value. I want to figure out capital M, which is the median value, and I'm going to actually ask you to integrate this function and make it equal to a half. And I'm going to let you do this as an exercise because I'm getting tired, but I know you're not. You have more stamina than I do. And if you quickly go ahead and do this, the answer M is... Oh, did you really think I was going to give it to you? You're going to have to do this yourself. Yeah, you will. So go ahead and do it yourself right now. I'm serious. Do it yourself. Press pause. Seriously, press pause. Okay, I'll give you the answer. 0.347 minutes. Or approximately 21 seconds. Now your notes are complete. Done.